Last time we finished up with the exponential model for growth. Today we want to take a look at a couple more models. And one of the things to remember about modeling is that we want to be able to translate English statements into mathematical statements. And so one of the popular ones we'll use, just to remind you, we had it up here as well. If A is proportional to B, right, then A equals K times B. And so let's try another model. If I can get this to go up here. And this model is called Newton's law of cooling. And what Newton's law of cooling says is that the rate of change of the temperature of the body is proportional to, now think about what it would be proportional to. If I have a hot cup of coffee in a cold room, for example, the temperature difference is going to be really big initially. And so how fast do you think the coffee will cool down? Versus, suppose that I have my coffee is approaching room temperature. How fast do you think it's cooling down then? So I think you might agree with me that the rate of change of the temperature of the body is proportional to the difference in temperature between the body and the environment. Okay, and that is Newton's law of cooling. Let's see if we can translate this into a mathematical statement. If we let U of t be the temp of the body, and capital T is the constant room temperature, or environmental temperature, then what is this saying? This part is U prime right here, and so is proportional to means that U prime is equal to K, that's my proportionality constant, times the difference between the temperature of the body and the temperature of the room. Good. Now, usually we want to write this so that the K is positive. So let's see if I've got this right. So suppose that I've got a very hot cup of coffee so that U of t is very large and t is small. Then will the coffee temperature be going up or going down? I think you'll agree it's going down. So if U of t is decreasing, U prime should be negative. But here, the way I've written it, right, it's going to be positive. So I would normally not write it like that. I'd put a negative sign in front of that, or I'd switch these. Either way. Okay, so for now we'll just put the negative sign out in front. Good. So now I think we've got everything right in that one. Let's see. Should we go through another model? Let's see. How about a freefall model? So people that have had physics will know how to do those. So in free fall, I've got a body falling in space, right? And so we're going to be modeling, well, before I get into that, remember that Newton's second law says that force is equal to mass times acceleration. And so if we want to write this model as a first order differential equation, acceleration is the derivative of velocity. And so our function here will be the velocity of t. So we'll take, let v of t be the velocity at time t. Then what do we have here? Well, gravity is force down, right? And so we'll have our force of gravity. Maybe we'll call it F sub g, right? Or F down will be mass times gravity. And then we'll have our Newton's second law. Then it says that F total, is equal to F. Okay. I don't like the notation I'm using here. Let me back up for a second. Because force down. I want to get my force up first. So what's our force up? Force up is going to be, I'm going to assume that the air resistance is proportional to velocity. So if we're moving quickly, there's going to be more air resistance than moving slowly. Okay, so in that case, we get that you can think of the force up as being mass times the velocity. I don't want to use. It is proportional to the velocity. It's not the mass. So that's going to, I need a different symbol. Okay, gamma. Okay. Good. Now we'll use our second law and say mass times the acceleration is equal to the force down minus the force up. Good. And so this is going to be our basic free fall model. Notice that that's a very simple model. We'll usually divide through by m. And also I should say that sometimes our book uses velocity squared. This is sometimes modeled as v squared, but that would have to be given to you whether we want to use the linear model or the quadratic model. Okay, so there's another model, and as a last model, I just wanted to mention what happens. You'll remember that our previous population model we had that the population, this is our exponential model, right? What happens if there's some kind of hunting going on? So that the population, there's a certain population that's removed every month. So suppose that, let's see, what symbol should I use? N members removed each time unit. So it's going to depend on whether t is, how we're measuring t. We want to be consistent. And so in that case, our p prime would just be, this is our increase, right? And then we would subtract our decrease. Good. And so I wanted to mention this again because we've seen three models now. Three models. Population. Just rewrite it here. P prime equals Kp minus N. We've seen free fall. In that case, we had M P prime equals mg minus gamma p. And we've also seen Newton, law of cooling, and that was U prime is equal to minus K times U minus T. Good. And what I want you to notice here is that all of these have the form y prime equals ay plus b. And so the idea here is that if I knew how to solve this differential equation, I would know how to solve all of these models. I would know a lot about population, free fall, and Newton's law of cooling. And these three topics are really not even related to each other, right? And so this is really the power of differential equations, that you're able to understand quite a bit about a relationship just by understanding how to get this general solution. Okay, and so that's what we're going to focus on next, is how to solve this differential equation. I will tell you that we'll be able to show this in just a bit, but our y of t is going to end up being our arbitrary constant, e to the at minus another constant, b over a. Okay, and so that is going to be the solution to that. And we will prove that very shortly. But I wanted to end here for now. See you later.